we'll move on. Section 3, the physical interpretation. I mean, you can say it's physical interpretation or a geometrical interpretation of the generating function. So we go back to the generating function in section 1. In the language of section 1, we wrote that as just the square root of this. The x variable x and t is over in, let's see what the infinity. Yeah, I actually write down the form first. 1 over 1 minus xt plus t squared, and then it's equals to sum over all this e sub n as a function of x e to the power n. Okay, and in our application, at least x is within the range of -1 to 1. Then, because we're doing an expansion, usually this kind of expansion only converge when, because x can take the value of 1, right? And this, in order for that this series to be convergent, then t is also less than 1, or t, or absolute value of t less than 1, right? And so, so this is like this mathematical result. We're saying that after this, there's several ways we can show that this object that defined as by this equation satisfy the Legendre equation. So you can look at the series solution and show that the series solution satisfy the Legendre equation. That's one of the homework questions. So, and then the other way is use this generating function to derive the recurrence formula, and then combining the recurrence formula show that the function that satisfy those recurrence formula also satisfy the Legendre equation. So that's another way to do it. And maybe there are some other way, like what Rager's formula and all that. Also, you can show that it satisfies the Legendre equation. So this kind of like a very abstract result. So it's just defined like that. You see, then this all these coefficient p sub n has this nice property that it actually is a solution of the Legendre equation. So that's kind of nice. But then this section is about a simple geometrical interpretation. I mean, you can apply it to a physics problem like an electrostatic problem, but it doesn't have to be. It's basically a geometry. Basically, you consider the three-dimensional space, right? Then consider two vectors. Usually, I think one vector along the z-axis, x, y, z, in Cartesian coordinates. So this vector is r, I think r sub 2 in I mean, it doesn't matter which one is, because they're symmetric afterward, right? And then another vector is arbitrary, r sub 1. And then this r sub 1 has this theta angle with the z-axis. Okay, so then now we consider these 2 points. So R1 minus R2 is this. So if the distance from these 2 points, R1 and R2, is this. That's the difference of the vector in absolute value, right? So you know that way. So that's just basic geometry. And now we look at the object. instead of the distance, we look at the inverse distance. R1 minus R2. Right, and now you can write like you can look at a different way. One way to do it is this cosine theorem, right? This make a triangle, right? The distance, this length is R1, so the length is the R1. So this length is R1 without the vector notation. This is R. So you can say this is the spherical. This is the radial coordinate of this vector or this point, right? And this is R2. The radial coordinate of this point R2, the vector point R2 is this scalar R2, and obviously both of them are positive. They are this length quantity, so it's positive. Okay, and now you can use the cosine theorem. Cosine theorem is this length square is right. You can, and then the length is the square root of this object is the R sub 1 square plus R sub 2 square, 2 without the vector square, and then minus 2 R1 R2 cosine the angle between the two vectors theta, right? And this defined as our spherical coordinate because we require one of them is on the axis. So this theta is just the spherical angle. Okay. So now you see that this is already very similar to this form, right? Except that we'll argue before that this x and t are all defined with the magnitude smaller than 1, right? And this is not quite like that. And also remember, we applied x equals the cosine theta for our physical application. So you automatically has this. You can say cosine theta is changed to x, right? And change that to x. But then you need to make this the other quantity. The first you have what you have a unity here, and then the other quantity should be less than 1. Like so if this is x, then whatever multiplied by this one should be less than 1. So you what you need to do is to choose which one is larger, or consider the both cases R1 greater than R2 or R2 greater than R1. So say if you have two cases, say the first case is R1 greater than R2. This is the picture. Right. If R1 is greater than R2, then you just pull out R1 square out, so it becomes R1, just R sub 1, outside the square root. And this become 1, and write this term first. This become minus 2 R2 over R1, right? And this cosine becomes x. And the other term is R2 over R1 square, right? Now this one is just the square root part is this one, right? Because you identify this is x2x. This will be your t variable. R2 divided by R1 is your t variable. So you have t and you have t squared, right? So compare, it's exactly this one. And now you satisfy the condition. Cosine theta office, you satisfy this inequality. And t also because we require R1 greater than R2, so this ratio is also less than 1. Right? And so, and now the second case obviously is just the reverse. Right? Put out R2, 1 minus 2, and now R1 over R2, x plus 1 over R2 square. Right? This is for O1 less than R2. It's okay. So, okay. Now you can combine the two and consider just your the larger and smaller notation, because now R1 is the larger. Compare R1 and R2, R1 is the larger. And this quantity, what we call T in here, must be the smaller one divided by the larger one, right? Likewise, this is R2 is larger for the second line. And this ratio is also the smaller one divided by the larger one. So you combine these two and write like one of R larger and then 1 minus 2 x R smaller over R larger with R smaller over R larger square. Okay, so this is just notation. So this you know this all this means, right? The subscript smaller sign and larger sign. It's just comparing R1 and R2, which one is larger, which one is smaller, right? So this object, what we start with, this geometrical object, the distance between the two vectors can be written as like that. And now the final line will be just applying this generating function. So it will be just all smaller. Oh, actually, generating function. It's just the square root part, one of R larger, and summing over n, piece of n, x is cosine theta, and then R smaller over R larger, n. Right? It's okay. So another way to write it is just put this together and then just separate the two denominator R is R smaller to the n power, the denominator R greater than n plus 1 power is n. Okay, either way. So that's the geometrical interpretation of the generating function. Now, after that, you can also say that this is, we talk about that this is the green function of the Laplacian operator, right? So here, green function for the free space, which means the no boundary except at infinity. R1, R2. I think this is for, I mean, depends on how you normalize it. I think this is for negative of 4 pi. I remember correctly. So some people define differently without the coefficient in front or the sign is different. But anyway, I think that is this one. So this for the free space and this object, the green function will be this green function is just 1 over the distance between R1. Right. So I think we went through that somewhere sometime before. Okay. So you can say that now with this interpretation, you automatically know you have to write down the green function. It's just exactly this one because the green function is just the inverse of the distance, which is now given by this formula. Okay, and now and also you can also for physical problem with this green function is still abstract mathematical object, but like if you for a physics problem, you can say you put a charge at R2 at the location R2, and then you try to find the electric potential at R1. So find R1. That is based on the charge at R2, and then whatever the charge is, Q, and then the potential by R1 is just Q over 4 pi epsilon 0 using SI unit and then the distance R1 minus. right? So another way to write it is this one. So now you can also apply it to this one, although it's that is actually a much simpler expression than this one. But sometimes you want to do it expanding in like all these functions, because this object might, I mean, abstractly it might be simpler to write down the expression, but when you do application like calculation, then like integration, sometimes using express it in series that involving simpler function like the power function of distance and the Legendre polynomial. It's not a very simple function, but then it's actually because of this orthogonality, so orthogonal property of this Legendre polynomial is sometimes doing integration using Legendre polynomial would be easier. So sometimes you want to do an expansion like that. Okay, and I think that's the first part. It's okay. So that's the geometrical property. It's okay. I think the next the second part of this section 3 is extending this idea to the so-called multiple expansion, and I don't think we need to go through that because we have a much more comprehensive way of treating multiple expansion in E and M. This is like very simple, almost just like introducing the idea. And for us, we can just look at that. If you have a charge distribution, whatever, even if just one point charge, just like that. If this is a point charge, then but you consider this is off the origin. It's not putting on the origin. Putting on origin obviously is simple, but you put it off origin, then the potential will be this one given by this one. If you consider observing it far away, so R1 will always be the greater one. R smaller is just R2 the location. So this is just R smaller is just R2. And this is R1. R1 is where you observe it. Right. They're always the different power. So there's infinite many terms, right? And then the inverse power of R. So any ratio is just 1 over R, and that is what we call the Coulomb potential. That's or the monopole term. Just like you put a charge at the origin, you get the monopole term, just 1 over R, right? For n equals to 1, the distance dependency is 1 over R squared. The potential depends on 1 over R squared, and that is called the dipole term. And the functional form is not just 1 over R squared. You need to multiply by the Legendre polynomial, R p sub 1, right? Because n is 1, so p sub 1 is just x, which is cosine theta. So this dipole term has the functional form of cosine theta, and then divided by R1 squared, right? That's the dipole term, and then you can keep going. So if you have n equals to 2, then you will have 1 over R cubed, and then multiply by p sub 2, right? And then so you have infinite many moments. So R1 this is dipole moment, and then n equals to 2 will give you this what do you call it, quadrupole moment, or something like that. So you keep going, and then but obviously doing this way is a little tedious, and also it's more restricted because we have restricted this Q on the axis, right? And generally there will be a distribution of charges, but you still consider far away and consider the potential. Then the potential will have all different moments. So you have zero, all the monopole, and then dipole, and then quadruple, right? And so, and that is the idea. And I guess that's not a whole lot for us. It's just the mathematical structure. Remember this Legendre polynomial is always multiplied by this radial dependence. So when you do multiple expansion, there's a functional form depends on the angular. For us, this is simple case. This is cylindrical symmetric case. So you have the Legendre polynomial. For the general situation, you multiply by the spherical harmonics. That is starting from next section, 15.4. Then we introduce the associated Legendre function, and then multiply by the angular, the azimuthal part, the e to the im phi, and you get the spherical harmonics. Right? And that is, use that to do multiple expansion for arbitrary distribution. Is that okay?